Okay, so this is not a single logarithm on this side. We have two logarithms, okay? They need to be combined together. Now, if we do this correctly, because we see addition between the logarithms, that means we need to multiply the x and the 7x minus 1. Now, we are still dealing with base 8, but I'm going to use a bracket just so you understand that I'm putting these two things together. Sometimes multiple parentheses kind of confuses people, but we need to combine by distributing that, right? We want to distribute this, and it equals 1. So we have log base 8 of 7x squared minus x equals 1. Okay? So let's change it to its other form, right? Because now it's a single logarithm. Something to the something power equals something. Okay, so base is 8, exponent is 1, and it equals 7x squared minus x. We're going to push everything over to the same side, so we have 7x squared minus x minus 8 equals 0. And we need to factor this thing. Either we're going to factor it or we're going to hit it with the quadratic formula, either one. If you want to use the Berry method like we did way back when, where we took the 7 times the 8, ironically I was teaching this to my son today for his Algebra 1 class. So we took the 7 times the negative 8 and got the negative 56. We factor as normal. Okay. What multiplies together to give us negative 56 but adds up to negative 1? Okay, and then the miracle of the Berry method, the 7 comes back in front of both x's. And then we look for GCFs that we can pull out and get rid of. I don't see anything in the first one, so 7x minus 8 remains. I do see a 7 in this one that I can get rid of, which would leave me with x plus 1. Now we want to know when that whole thing, equals, stop, I didn't say touch the outside edge. We want to know when that equals 0. And so we set each one of the factors equal to 0. You know, set that one equal to 0, set that one equal to 0. And so we know that x equals negative 1. And that's an easy one, right? And 7x minus 8 equals 0. That's 7x equals 8. X equals 8 over 7. Now, what is going on? Okay, so do either of those cause a problem? All right, I'm going to come back over to the original. So we had 8 over 7 and negative 1. Do either of those cause a problem? Well, right here I have a problem when I plug in negative 1. Because log base 8 of x, that is just a plain old logarithm function with a domain of greater than 0. Well, negative 1 doesn't fit in there, folks. Remember, you can't plug negative 1 into that because there's nothing over here. All right? So this is a bad answer that needs to be thrown away. Now, 8/7 is going to work, because I can take the logarithm of 8/7, plus I can come over to this other one, 7 times 8/7 minus 1. That's going to be 8 minus 1, which is 7. Okay, we're still good, because you're still taking the log of the number 7, and that's totally legit. Okay, so the only answer to the question is 8 over 7, not negative 1. So I guess we did run into a situation where we had to reject a value. Okay. Notice that was where we had a quadratic where we had to factor it. Okay, so I see another addition. So to make a single log on the left side, I'll have to multiply the x plus 23 times the x plus 5. And that equals 5. Okay, so that would be log base 3 of x squared plus 28x plus, what is 5 times 3? 115. Now we have it as a single log, so we can change it to its other form. Base exponent equals something. Base is 3. Exponent is 5. What it equals is x squared plus 28x plus 115. So 3 to the 5th. Wait a second. 3 to the 4th. That's 243. So we have to subtract 243 from both sides. Okay, let's hope this is factorable. X squared plus 28x. 115, take away 243. 115. Take away 243. Negative 128. So can we come up with factors of 128 whose difference is 28? Ooh, gonna have to practice with this. Factors of 128. Well, 128, let's say divided by 4. That's 32. Well, doggone it, I found it. Because they have a difference of 28 units. So we want x plus 32 and x minus 4. So the two possible answers are negative 32 and positive 4. You know, if you set each factor equal to 0 and solve it. But if I take that negative 32, I don't really care if I plug it in there or plug it in there. I'm going to end up with a negative number, and you can't take the logarithm of a negative number because from the graph we can see that the domain is greater than 0, which means there is nothing on the other side. So that doesn't work. 4 is the only good solution. And man, I hogged up all my space for question 16. So in this particular question, though, I have 2 logarithms, one on each side. So I do have single logs. But what I want you to do to see here is, notice that these are both logarithm base 7. Now, if the log on the left equals the log on the right, which that sign in the middle guarantees that's true, then what do you know about x plus 7 and 12? Doesn't that mean that x plus 7 has to equal 12? And the only way that could happen is if x is 5. So that one actually was easier than a lot of the questions. Once again, we can talk about it. Do we have single logarithms on both sides? You can clearly see these are not. So let's see, I have log of x plus 14 on the left side, and on the right side I'm going to have to multiply that 14 and that x, so that's log 14x. Now this is a base 10 logarithm all the way through, so as long as the bases are the same, I can compare those those arguments of those logarithms. They have to be the same also. And then, of course, we can take 1x away from both sides. 14 equals 13x. And divide by 13. So 14 over 13. And if you go plug them in, you will find that you don't have any basically extraneous solutions would be the term. Okay. So let's see. Let's put them together. So we have log of 3x minus 8 on the left side. And I'm going to multiply the 4 and the x plus 2 together. That would be log 4x plus 8. If the bases of the logarithms are the same, which is true, they're both base 10, then the arguments are equal to each other. And then we can move the x's to one side, and move the constants to the other side. And we end up with x equals negative 16. Now, if I take negative 16 and plug it in right there, that means I would have log negative 16 plus 2, which is log of negative 14. But if you think about the exponential or the logarithm graph, negative 14, that's way out here. It's not even, there's nothing there. So that means there is no solution to this question. Just because you find an answer doesn't mean that you don't have to test it by plugging it back in. Okay, 19. Move your exponents. So we have log of x to the 6th equals log 64. Okay. If the logarithms have the same base, then these arguments have to be equal to each other. And then I can instantly get rid of the 6th power by taking the 6th root. And I believe the answer is 2. I know we're practicing a lot of problems, but I think this will be helpful to you. So I see that we are dealing with subtraction. Now we still need a single logarithm on that side, but because it's subtraction, that changes to division. So the first part is the numerator, and the second part is the denominator. And the other side of the equation, well, that already was a single logarithm. Now, if the left side and the right side have the same base, then I can pretty much ignore the term log, and 10 or x plus 10 over 2 equals 4x plus 2. Now, we know that anything can be divided by 1. That's a proportion. We can cross multiply, and we should. Now, if we cross multiply, we'll get 8x plus 4 equals x plus 10. And we can subtract 7x to that side, or 1x, leaving 7x. Subtract 4 to the right side, and that gives me 6. And divide by 7. And we know that we have 6 over 7. And that doesn't look like it would cause us any kind of problems if we plug it back in. Question 21. Single log over here. We see addition in there, so that means we multiply the x and the x minus 6. So that'd be x squared minus 6x equals log 7. since there's two equal logarithms, then that means the arguments have to be the same. And we could bring this to the other side, x squared minus 6x minus 7 equals 0. So x and x minus 7 and plus 1. So the two possible answers are, if we set those factors equal to 0 and solve, 7 and negative 1. Do either of those cause a problem? Well, 7 looks like a good solution, right? If you plug it in, 7 does not harm anything. But negative 1 has a problem right there. So actually, it would have a problem with both of them, so we can't have it. 7 is the only correct solution. Okay. Suppose that a new employee starts working at $7.79 per hour and receives a 3% raise each year after time t in years. His hourly wage is given by this equation. Find the amount of time after which he will be earning $10 an hour. So the 10, that's the y value. Well, the first thing we want to do is divide by 7.79. And 10 divided by 7.79 equals 1.284. 1.284 equals 1.03 to the t power. Okay, now it is time to change it to logarithms. We got log base something of something equals something. So the base of the logarithm, 1.03. I need to zoom in on this. My fingers are too big. The exponent, all right, that goes next. I can put that in there. And then the last thing that's left is 1.284. Now, my calculator won't do that the way it is, so I'm going to have to use the change of base theorem. Log of 1.284, log of the big number, log of the argument over log of the old base. And so now I can go to my calculator. Log of 1.284 and parenthesis divided by log 1.03. Oops, that's 1.3. Okay, 8.5 years basically. Time equals 8.5 years. Okay, so complete the table for a savings account subject to 2 compoundings per year. All right. Let A represent. Okay, so we're starting with 10,000. We want to end up with 19,000, and we want to know how much time it'll take to do it. All right, so we have 19,000. Oops, I probably should zoom in a little bit here. We got 19,000 is how much we want to end up with, starting with 10,000. 1 plus 0.0625 over 2. Man, I ran out of room. Okay, so I'm gonna have to squeeze my exponent in there. See if I can. I know it's n times t. We'll call it 2t. They told me that n was equal to 2. That would be the term semi-annual, but we'll use more things like quarterly, monthly. Okay, they want to know when that's going to happen. So first, oops, don't slide it out of the way. Divide by 10,000 first. So that's 1.9 equals, alright, so I'm going to have to figure the other side out here. 1 plus 0, what was it? 625. 625 divided by 2. Now I raise that to the, actually, 1.03125. 1.03125. Raised to the 2t power. Okay, so now I can change it to logs. The base is 1.03125. The argument is 1.9. What's it equal to? 2t. And we want to do the log of the argument over the log of the old base, using that change of base theorem to change it to something that's easier. And so, come over to the handy dandy machine. Log 1.9 divided by log 1.0315. Oh, 125. Oh, I missed the 2. And I even noticed that I did that over here. Let's get that 125. That's 20.86. 20.86 is equal to 2t. That means 1t is equal to 10.43. We can check that out. Divide by 2. 10.43. In question 24, we are going to be finding the annual interest rate. We will have everything else we need. They're telling me that my compounding factor is 180. That's almost every other day. So, amount invested 1,400, and we want to end up with 1,900 when we're done. 1 plus r over 180 to the 180 times 2 power. And I ran out of room for my last parenthesis. So, of course, we're going to divide by 1,400. 1.357. That exponent is 360. So how do I get an exponent of 360? Take the 360th root. Yes, folks, I know that's a pretty ridiculous root. So on my calculator, I did the 1900 divided by 1400. Now I'm going to type 360 math and the fifth one in the list. Come on. Okay, so this is now going to be the 360th root. I'm going to put of the answer, that way I don't have to retype the last part. Okay, so we got how many zeros were there? 3. Okay, where'd that go? Let's see, 5. Okay, that equals 1 plus r over 180. Okay, so if I subtract 1 from both sides, then we have 0.00085 equals r over 180. Once again, this is just a proportion. Cross multiply. Okay. 180 times 0.00085. So if I solve that, I get an r value of 0.153, or 15.3%. That's pretty good. That's really good, actually. Okay, last problem for this lesson. And if we're done with this, then you are, we have all the notes that we need for the test. Here's a function. It models the percentage of students who could recall the important features of a classroom lecture as a function of time. Now, what you should be seeing is that as time goes on, important things start being lost from our memory. X represents the number of days that have elapsed since the lecture was given. Figure shows the graph of the function. After how many days do only half the students... Now, one thing I want you to realize about this particular model is that they're saying that 50% of the students, you leave that. P of X is actually a percentage. You don't have to change it to a decimal. So we're going to put 50 equals 80 minus 25. Oops, 25. Log base 2 of X. So, yep, subtract the 80. So that'd be 30 equals negative 25. Ooh, negative 30. So divide by negative 25. And so let's see here. What is 30 divided by 25. 1.2. So we have 1.2 equals log base 2 of x. So it's a single log. We can change it to its exponential form. The base is 2. The exponent is not x. Oops, I lost my g. Uh, 1.2, and my exponent, or the argument is what it equals. So, come here. We have 2 to the 1.2. 2.297. 2.3 days. After how many days do only half the students recall the important features of the classroom lecture? 2.3 days. Locate the point on the graph that conveys this information. Well, let me zoom in on the graph. So 50%, you can see that it's a little bit more than 2. That is the coordinate. 2.3 comma 50. 2.3 days, 50% of the students can remember what's going on in the class, or the important features. Okay, and that's the finish of these notes for the chapter.